Sure. Well, welcome everyone to the EC 590 seminar. It's good to see folks from outside the department as well today. And that's because we have a very exciting talk. So we all know how, well, the promise of fusion, abundant, sustainable, clean, safe. I mean, so many ways to describe how great it is. And, it's long been recognized as a great technology of the future, right? And the running joke, of course, is it's always going to remain there. But it looks like the right enabling technologies are coming together to make a practical system possible in the next few years. And one of the groups that's working to make this happen is Commonwealth Fusion Systems, a spin-off from MIT. And we are fortunate that we have one of the principals from CFS, Dr. Brandon Sorbom, to talk about the efforts, specifically on the plasma containment with the high field superconducting coils, which some people in the audience today are especially interested in. Dr. Sorbom holds a doctorate in nuclear science and engineering from MIT. He co-founded Commonwealth Fusion Systems and was named to the MIT Technology Review's list of 35 innovators under 35. He leads CFS's work on the development of the technology for commercial fusion devices. So let me turn it over to Dr. Sorbom.
Great, thank you very much for the introduction. It's a pleasure to be here. I wish I could have been there in person, but
so do we.
Whom we'll have to do. So I changed the title a little actually because I was asked to give a little bit more of an intro to a background on fusion as well. So I will, so not to worry, I am going to talk a lot about the high field superconducting magnet technology, but I thought I would, spend maybe, sort of the first third of the talk just going over fusion and, what fusion is and kind of like what we're trying to do. So before I start, I just wanted to have some acknowledgements. There's a whole bunch of people. Actually, the list is even much longer than this, but there's a lot of people. This is primarily the team that worked on the magnet technology that I'll talk about. And in particular, Zach Hartwig is a professor at MIT. I also pretty liberally stole content from slides that he gave at a conference last month because I thought that encapsulated a lot of the magnet work pretty well. So really high level, I think this doesn't really need that much explanation. We need a new source of clean energy. And also kind of as an aside, we talk a lot about clean energy. We basically, we want to mitigate climate change. But there's also an interesting corollary with fusion where if you look at, you can choose your favorite index of, things that make people's lives better. So like the UN Human Development Index, but you can track a whole bunch of things and you find a strong correlation with energy use per person. And so unfortunately, there's also a strong correlation because a lot of energy is fossil fuel produced at this point. There's a strong correlation with CO2. But I think there's a really interesting point with this that as opposed to other sources of renewable energy where we're trying to just, kind of get our heads above water and break even by getting clean energy, there's this added piece of fusion that I believe, that our company and our effort believes, that not only do we want to get to a place where we're not polluting anymore, but we actually want to get to a place where we're increasing the amount of energy that people use, because there's lots of things that get better when you have sort of an abundant source of energy. You can think of, like, for example, access to clean water is a big issue around the world. And if you had access to abundant energy, you could make desalination a lot more practical and affordable. And there's a lot of things like that, where if you had more energy that was cheap enough to be affordable, you could do a lot of really great things beyond just mitigating climate change. So high field fusion, what exactly, so fusion, like as the old joke was mentioned, is always 30 years away. But what actually is fusion? So in a nutshell, fusion is it's the power source of the universe. It's what powers all of the stars and the sun that you see in the sky. In terrestrial fusion, so the sun works on hydrogen, a hydrogen fuel cycle. On Earth, we actually want to use isotopes of hydrogen called deuterium and tritium here, which combine to release energy, which is in the form of an energetic helium nucleus, has 3.5 MeV worth of energy, and an energetic neutron has 14 MeV worth of energy. And if you kind of walk from an ideal case where if you could somehow take a star and put it in a bottle, you generate heat from that star and then put it through a power conversion system to supply electric power to the grid. So that's, you know, very idealized situation. Going to a cartoon, there's a myriad of ways that people have looked at in trying to confine a star like this that I won't, that's the subject of a whole nother talk itself, so I won't go into that. But the type that we're focused on, which is called a tokamak, is basically this magnetic bottle that confines the plasma. And this is kind of a cartoon of a tokamak. So there's these D-shaped magnet coils that confine this plasma in red, and then you have your various inputs and outputs. So you have, you know, deuterium and tritium fuel coming in, and then you have heat coming out in some kind of a loop that goes into a heat exchanger, and then that powers a turbine generator. And this is a little bit more fleshed out of, this is actually a CAD drawing of, at a very high level, obviously it's missing a lot of detail, but very high level CAD drawing to scale of Alcator CMOD, which was a fusion device at MIT that ran for the last 20 years and it was recently decommissioned. And the plasmas that we make in these machines are actually routinely much hotter than even the center of the sun, which is really interesting. Actually, tokamaks, especially tokamaks that have cryogenically cooled magnets, have the steepest temperature gradient in the solar system, which is kind of cool. You go from, you know, 5 times hotter than the center of the sun here in the plasma to less than a meter away, you have cryogenically cooled magnets. So really quick, I'll walk through the fuel cycle. So like I mentioned before, you have deuterium and tritium that you combine. You get an energetic helium nucleus, which is confined inside of the magnetic fields and goes back to sort of self-heat the plasma and keep driving this reaction. And you also get this energetic neutron. And so the neutron, because it's, you know, it's not charged, it flies out of the magnetic confinement, and you surround your vacuum chamber that has the plasma in it with what we call a blanket. And the blanket is basically just a liquid. It's a working fluid. In our case, we're thinking about using various different types of molten salts. And the neutron basically collides with atoms of the molten salt, bounces around and deposits its energy and gets the salt hot. And then you can put that through a heat exchanger and run a turbine and a generator. Another thing that the molten salt does, which is why we use that instead of, for example, water, is that you also want to breed tritium. So deuterium is naturally occurring. There's, depending on how you do your calculations, somewhere between 100 million and 1 billion years worth of fuel of deuterium that you can get from water. It's 1 part per, I think 1 in every 6,000 H2O molecules is actually a heavy water molecule. And so it's very cheap. You can run some quick calculations to show that, you know, powering a city like Boston would require, you know, $10,000 worth of deuterium per year. So it's effectively free. But the tritium, on the other hand, actually has a half-life of about 13 years. And so it decays, and you have to make more of it. And so what you can do is the neutrons, as they bounce around, they will actually breed tritium inside of this blanket. And so you can extract that tritium and put it back into the system. So the helium nucleus goes back and it transfers its energy to the deuterium and tritium. But also, when the helium gets cold enough, it'll start generating photons that radiate power. And it'll also collide with, eventually, it'll reach the sort of the outside of the confinement of the plasma, and it'll hit the walls of the vacuum chamber, which are in contact with this blanket, and then again heat the working fluid in the blanket. And these are both the same turbine and generator pairs, but it's just showing kind of how the energy actually goes from, you know, from the particles that you make in the fusion reaction to actually being, you know, turned into heat and then electricity. So fusion really is actually, you know, it's a really fancy heat source. It's kind of funny that, you know, fusion is, these machines are very, very complicated, but at the end of the day, it's really just another fancy way to boil water, or in our case, molten salt. And so the conditions for burning plasma, so that's the thing that's inside of the vacuum vessel, have actually been really well known since 1955. It's called the Lawson criteria. And there's three things that you need. You need to have enough fuel density, which is actually, when you run this number, it's actually it's a very large number, just in absolute units, but it's a very small number compared to, for example, the density of air. The fuel inside of a plasma is about 100,000th of the pressure of air. So it's very, very tiny puff of fuel that you need to get in. But nevertheless, you need something to burn. Then you need the temperature to be hot enough, so about 100 million degrees, or for those who like to think in plasma physics units, about 10 kilo electron volts. And then you need energy confinement. So you basically need to insulate this plasma well enough so that the alphas that you make can go back and can keep the plasma burning. And so this Lawson criteria is kind of, it's this figure of scientific merit that's been known for a long time. And it's fundamental, but it actually doesn't say anything about economics, which is really important if you want to actually sell electricity. So just looking at the Lawson criteria, and going back to this, this idea of fusion always being 30 years away, with Tokamaks, it's really interesting actually that there's actually been an astounding amount of progress. So on the y-axis here, we have, this is a log scale, we have the triple product with units of atmosphere seconds, and then on the x-axis is just the year. And so in 1969, just looking at MIT machines here, there's actually been about 170 of these Tokamaks built around the world. 1969, we were right here. So triple product needed about a 30,000x multiplier to get to break even. So another term that we have is Q, capital Q, which is the plasma gain. So this basically means before you get to a fully burning plasma, you inject some radio waves into the plasma, or you drive current through the plasma to heat it up. And the power that you have to put into the plasma is obviously like a parasitic loss. And so Q of 1 means that the amount of energy that you get released from the DT reaction is equal to the amount of power that it takes putting into, the amount of energy that it takes to put into the plasma to make it burn. So you want to get to a Q of greater than 1 in order to have a power plant. So walking forward to Alcator C, 1978, you see there's a whole bunch more points, and notice that so this is linear on a log graph. So this is actually really, really fast improvement in the triple product. And at this point in time, we're about 100 times from getting Q greater than 1. And let's go forward again to Alcator C mod in 1993. This is actually, I think, this goes a little bit later than that. This is just sort of a smattering of Tokamaks. And you can see we really rapidly climb the curve. And I didn't include it on this graph, but for those of you who are familiar with electronics, Moore's law, this actually beats Moore's law. So Moore's law relates to how fast processor speeds basically double every 2 years. And this actually beats the triple product improvement up until about the year 2000 beat Moore's law. But obviously it's not the year 2000 anymore, it's 2020, and we still haven't crossed this threshold. And so why? And what happened was that what this plot doesn't show is that these devices were getting bigger and bigger. And so ITER, which is the next step, which would get, which would get above break even, actually get to a Q of about 10, is a very, very large device. So it's actually the largest science project in the world right now. Nobody knows exactly how much it's going to cost, but estimates range from somewhere between 25 billion to 50 billion, depending on who you ask. And it's a very impressive machine, but it's very large. And so it's taking a long time to build. And that's why, this curve kind of flattened out. So we looked at this and said, is there another way to clear this hurdle of Q equals 1? And so let's dive a little deeper into the triple product plot. So before, we were putting all the triple product together. So density, temperature, and confinement time. Actually, if you break it into n tau, which is the density times confinement time, and then the ion temperature, which is T, and you plot contours of constant Q, you get something like this. And obviously moving into the upper right corner of this graph has been the goal of fusion energy for about 60 years. And as you go through these regimes, you can almost think of it like Mach numbers. So a Mach number being like how close you are to the speed of sound, changes, kind of fundamentally changes when you build things that are at different Mach numbers. The physics will change. And so when you climb up this, you have to be really careful that if you're all the way down here, that you don't make extrapolations that say, oh, you know, if we're, say, you know, we have this density and confinement time and this temperature, you can just extrapolate all the way up, because just like Mach regimes, the sort of the confinement regimes that you have in the plasma will sometimes change. And this has sort of been, a very painful realization that's happened several times in the history of fusion. And so you can kind of separate this plot into three regions, where if you're Q equals 1, if you think of this like a roller coaster, this is like, yes, you can ride this ride. Physics has been unquestionably demonstrated, and reactor engineering is should be mature or maturing. And now you're looking at economics. If you're sort of in the Q of 0.1 range, the physics is pretty much there, because you don't have that big of a difference in the Mach regime, if you will. And if you're down here, the fundamental physics is still a long way from being able to show that you can get to Q greater than 1, and you need to sort of push into this regime before you can make any claims about reactor engineering or economics or anything like that. And so going back a little bit, so the magnetic field confining the plasma really sets your performance. So if we look at the triple product again, NT and tau, you can reduce it into a few parameters in the plasma. And don't worry, I'm not gonna go into all the math here, but these, so the beta normal, this H factor, this Q star factor are plasma physics parameters, which are relatively, to first order, these are sort of, these are similar, at least in tokamaks, of what you can achieve, regardless of the machine. So you have two other control knobs. You have R, which is the major radius of the device, and you have the field, which is the magnetic field on the axis of the plasma, not at the magnet, which is higher for a tokamak, but right at the plasma. And you see that the energy gain, which is sort of the science feasibility, goes as if you keep these plasma physics parameters constant, you can either make the machine bigger by increasing the radius, and you get kind of linear gains with that, or you can increase the field and get gains to the power of 3. And if you look at the economics, which is the power density, you have same dimensionless parameters. This is an aspect ratio parameter of the device, inverse aspect ratio. You keep these constant, you look at the scaling, you get a linear scaling with size again, and this time you get b to the power of 4. So you can see that the magnetic field that you use, which is your insulation, is really, really important. You get these huge wins if you can just squeeze a little bit more magnetic field out of your magnets. And so going back to this triple plot graph, here's a bunch of points from different devices. And these are all tokamaks, all these blue points here. And in the past, we've achieved really high performance in small devices because we used really high field copper magnets. So Alcator A, you can kind of see a person here for scale, small device, but it was 10 Tesla on axis. And Alcator C was even higher on axis, it was 12 Tesla. And so, this was actually, even though you might think of copper magnets as kind of low tech, I mean, you can take a copper wire and wrap it around a nail and put the ends on a battery, and you have a little electromagnet. This was actually like state-of-the-art, cutting-edge copper magnet technology. So they really figured out these really great feats of engineering to get these copper magnets, so you could really just push them to the limit. You're basically running them in a condition where you're able to cool them fast enough so that the magnet doesn't melt as you're pumping mega amps of current through it. And because these devices were so small, they were able to be built relatively inexpensively by a small team that was on a single university campus, which is really cool. And so if you look at this plot again, Alcator A and Alcator C achieved pretty high performance compared to other devices here, which were larger. And actually Alcator C mod, which was the latest machine that had been built at MIT, had very similar performance to, at the time, to other devices that had been built that were much larger. So if you look at JET or JT60, in Japan and Europe, respectively, those devices were operating at lower fields, but were much, much larger. And CMOD, even though it was much smaller, these are all to scale, it had an 8 Tesla field on the center of this plasma. And so it was actually able to get very similar performance to those devices. So another way of looking at this is to say, so here's this R, so the major radius, just the definition of that is the distance from sort of the center of the tokamak. So if you think of a tokamak as a donut, it's kind of the center of the donut hole to the center of the plasma. That's what we call capital R, which is the major radius. And so if you plot major radius on the y-axis here, you can kind of group it into 3 sizes of machines. So sort of anywhere below 2 meters major radius, you're building a device that's at a university or company scale. So with sort of like a single organization, you could build a device like this. From sort of 2-ish to 4-ish, maybe a little larger than 4, you could build in a national lab of a large country. So like JT60, you know, in Japan, JET in Europe. In the US, we actually built a machine called TFTR, which was in this size range. And then higher than that, sort of like past 4.5 meters major radius, you're really looking at a massive device. And that's really a global scale, which is why ITER is this huge international collaboration. So on the y-axis here, we have the magnetic field, again, on the plasma, not on the magnet. So the field on the magnet is roughly in a tokamak. Rule of thumb, you can sort of multiply this number by 2 to get the highest field that the magnet generates. But what you really care about for plasma physics is the field that you see at the center of your plasma. So that's what this number is here. And if you plot contours of constant fusion gain, so if you go back to this plasma physics parameter Q, these contours, this doesn't look like a very complicated plot, but these contours are sort of taken by looking at all of the machines that we've built, all 170 tokamaks in the last 50 years, and condensing the physics, you get these contours of constant Q. And these are, even though we haven't built machines, you know, larger in this case than sort of 4 meters major radius and higher field than 12 Tesla, we have a pretty good idea of how the physics is going to perform of those devices. And now, if we look back at the magnets, you can say, okay, well, we built devices with really high field using copper magnets, but for a power plant, you know, thinking back about how you make those copper magnets run, you have these very large resistive losses. And if you actually want to make electricity, you'll never be able to build a tokamak out of copper magnets and make it economical. There's no way that you'll be able to build a copper magnet that does that. So you have to use a technology called superconductors. And so superconductor is something that passes electricity without any resistive losses. And LTS stands for low temperature superconductors, which is sort of the first generation of practical superconducting technology. And unfortunately, the operational limits of LTS magnet technology is around, you know, 12 to 15 Tesla on the coil itself, on the actual, you know, the superconductor, which limits you to sort of a field of 6 Tesla on your plasma. So if you're using LTS, that means that this entire space of the graph is not accessible to you. And really, the only space that's accessible for net energy fusion, so where you have, you know, Qs of, you know, 10 or greater, is kind of up here. And that's where ITER sits. So ITER was designed in the 80s when LTS was the state of the art in superconducting technology. And what they did is they constructed a plot similar to this one and said, okay, let's build the smallest machine that we can given the field constraints that we have. And that's what they did. And you can see ITER is still a very, very large device. It's difficult to see in this picture, but there's a person to scale right here. You can see compared to like CMOD or Alcator-C, where there are people sort of, you know, standing next to the machine, you know, this person, you can barely see them because they're dwarfed by the machine size. But if you use HTS magnets, you can actually open up the whole side of this graph and say, instead of building at the same, you know, contour of Q, instead of building a device that's this big, you can raise your field and build a much smaller device, which is exactly what we propose doing. So the first sort of design study that we did all the way back in 2012 was on a device called ARC, where we said, okay, let's just match the fusion power of ITER and see how small we could make a machine that made electricity that got the same fusion power as ITER. And because your blanket, which is that liquid that surrounds your vacuum vessel, needs to be a certain thickness, that sets another limit to sort of how small you could build a power plant. But this was really just sort of a thought experiment. I mean, we published it. It wasn't, it was definitely not a shovel-ready engineering design, but it was, an engineering feasibility argument for showing, or a physics feasibility argument showing that you could build a device that was much smaller than ITER, that got the same fusion power and actually had enough room for a blanket so that you could convert that heat from the fusion into an electric power. And taking that a step further, you could say, well, what if you actually stripped out the blanket and you didn't worry about making electricity? Now you could actually design a device like Spark, which would be a net energy device still. So you'd have a Q greater than 1, but it would be even smaller than ARC. And this would be very, very small. These devices are all roughly to scale. So you can see Spark, which sits out here and will be a net energy device, compared to ITER, is very small and is sort of in this regime where you could build it with a single entity like a university or a company. So that's sort of what fusion, very, very high level. I mean, each of these slides could probably be expanded into its own talk, but very high level overview of fusion and why we think that high field is really the way to go if you want to get fusion economical. So what MIT and CFS have been doing for the last 2.5 years is we've been developing the technology to say, okay, we've been talking a pretty big game about how high magnetic fields make everything better, but nobody's actually built the magnets yet that can achieve these fields out of HTS. The superconductor itself exists, but nobody's actually built a magnet to scale. So there's been a very large research program that has gone on something that we call Viper. And this is basically taking these tapes of HTS. The HTS comes in the form factor of like a flat tape. It looks kind of like a copper ribbon, and putting it into a format where you have a cable that you can put multiple tapes into, and you can cool it. You can make it stable to things like Quench. You can make it robust and manufacturable. So that's what I'll spend the rest of the talk going through. So Viper, it's a little bit of a backronym, chose a name that we thought sounded good. It stands for vacuum pressure impregnated, insulated, partially transposed, extruded, and roll form. So a little tortuous, but kind of works as an acronym. And for the next set of slides, just to sort of guide your eyes to what risks we're trying to retire, there's sort of 5 main classes of risk. So there's fabrication, which means can you build enough of it to actually be a robust process that you could make into magnets. There's joints, which is how do you go from the termination, basically the interface between the superconducting cable and the resistive necessarily connection that you have to your power supply. So you want to make that as low resistance as possible, because any amount of resistance means that you're basically bleeding heat and power, which is bad. Something called I cross B. So I cross B loading. So those of you who've sort of taken basic physics, there's something called Lorentz Force, where if you have a current that's moving inside of an area where there's a magnetic field, you get a force. And it turns out that the currents that you put through these cables and the fields that you're putting them in lead to very, very large forces. And so you need to show that these cables aren't going to shred themselves with the cyclic loading that we put them under to operate in a Tokamak environment. So Spark is going to have magnets that sort of reach around 20 Tesla on the magnet itself, or a little higher. And so that's the space that we would be operating these in. Strain is another related to the stress, but the axial strain, if you pull on these cables, they need to be able to handle strains around 0.3 to 0.4%, which would be equivalent to what the Spark magnets would feel. And then finally, there's something called Quench, which is when your superconducting cable, say there's an off normal event, and like say the cooling somehow got turned off. A quench is when your superconductor all of a sudden goes normal and stops being a superconductor, and you bleed these really, really large amounts of current into the surrounding material, which is resistive. So quench means that you can design a system that can tolerate one of these events without basically burning your magnet. So in order to do this, we built about 20 cables ranging between 1 meter and 12 meters in length, did a whole bunch of in-house tests, and then we did 4 separate tests at a facility in Switzerland called Sultan that helped us retire a lot of these risks that required something like a magnetic field or doing quench tests or things like that. And so if you look at the bottom here, just to sort of guide your eye to what risk we were working on, this is sort of a visual guide to that risk. So really quick, at a high level, what does Viper actually look like? So it's based on this thing called Twisted Stack, which was actually developed also at MIT and extended by a group at ENEA in Europe. And basically, Twisted Stack is where you take if you're looking end on in a cross section, you have a copper former, we call it, where you twist the former and then you load each of the channels in the former with tapes. So you can see stacks of HTS tapes inside of this former. And then critically, for our process, what we determined is that in order to make sure that this is mechanically robust and thermally robust, we actually fill these channels with solder. And so this basically becomes sort of like a monolithic structure where you have these solder-filled channels that are embedded with a whole bunch of tapes, and it's also twisted. And then in the center is a hole that you can put coolant into. This is another reason why you want to have a copper former, because you need to have some way for the coolant to talk to the HTS, which is the thing at the end of the day which needs to be cooled. You have a copper jacket around that, and then depending on the design, you would have a stainless steel jacket around that for mechanical stability. You could also use a steel radial plate though, similar to like how ITER does. And this is just one of the joint concepts that we have, which is called a saddle joint, where if you had 2 cables like this and you wanted to terminate them or join them, you could press them into a saddle that's filled with indium to kind of fill all the voids in between and use that as a joint. So the vacuum pressure impregnation, so that's the V of Viper, is one of the critical pieces to this whole process. And so this is kind of a blown up SEM image of what one of the channels looks like after. So we made one of these cables and then we chopped it up and we put it under an SEM, and this is what it looks like. So each of these things here is a piece of HTS tape. You can see that there's solder here. And what this does is it gives you 3 things. So it gives you mechanical strength, because now instead of just kind of sitting in here, they're physically joined to each other and to the former by a material. You have thermal stability, because now, again, instead of just sitting in this channel, if these guys start to go normal, or if you have heat from somewhere else, it can easily transfer. The heat can be passed through the solder to the copper, and you can carry the heat away through the cooling channel. And then finally, in order to make good electrical, this is what normally what people think about with solder, is that you have really good electrical connectivity throughout the cable. So if you have like a manufacturing defect somewhere, or you have a quench starting in one point, the current can reroute itself much more efficiently. So I realize I'm going through this a little fast, but I want to make sure that we get to all the tests that we did. So one of the first things that we did is fabrication. So we wanted to know that as we, instead of just building like little test samples, we needed to know that at scale, these things were going to work. So we actually did 2 sort of large fabrication tests following these smaller subscale R&D tests, which we don't present here, but we did, I don't know how many tests of, very short sections of cable that we bent and twisted and, did all manner of things to see how it would survive. After we did that, we did a 12 meter cable that was put in a liquid nitrogen bath at MIT and put current through it. And we also built a 5 cable assembly. It's kind of hard to see in this picture where the cables go, but these were sort of if you think of this as sort of a 2-dimensional coil where it's just sort of one pancake wound. This coil is actually, you can see there's actually 3-dimensional geometry in these bends that are going through the current leads here into a circular, into one sort of loop of cable, which was originally intended to be put in a field at a facility in Japan. That unfortunately didn't pan out, but this was a sample we built for it, and we were able to actually take that sample. Here's another picture of it where you can see the leads a little better. We built our own very large liquid nitrogen cryostat, and dumped this whole thing and put current through it. And we were actually able to confirm at the liquid nitrogen temperatures, we were able to confirm with predictions that the critical current that we got to, so if you measure the voltage and the current of this, critical current is where your voltage equivalent goes to a microvolt per centimeter. If you, it's really an electric field criterion. We were able to basically predict a critical current of around 6.2 kiloamps, and we got actually a little bit higher than that for the actual measurement that we did. And so that said, when we fabricated this whole thing and we bent it into these crazy, three-dimensional shapes, we didn't actually damage any of the HTS, and it all sort of survived all of these manufacturing processes that we did, from the bending to the rolling to the impregnation with solder. Didn't show any degradation there. So then, after we were confident that we could actually, build these things, there's a facility in Switzerland that was actually built for ITER, to qualify the ITER conductors of LTS, but could also be used just as applicably for HTS to carry out some of the other tests that involved high magnetic fields and very low temperatures. And we made 4 samples. So there's Alpha, Bravo, Charlie, and Delta that all did basically risk retire different aspects of the cable. And so the first one was really kind of a shakedown. We didn't really know, we had an idea, obviously, of what to expect, but it was really, this was sort of the first one that we were doing, and we were kind of, we were hoping that the cable didn't shred itself and that all of our models worked. And it turned out that our models worked very well, and we were able to, here's, if you look at the experiment versus the model, we were able to match pretty closely what the critical current was of both the experiment and the model going into these tests. So, we were sort of within 2 to 4%, which is really good given the uncertainty going all the way back to just sort of the data that you can get on the HTS tapes themselves. So the next test that we did, Bravo, is we built another one of these samples, and this one was, we were really focusing on the joints. And so I mentioned before, the joints are really important for both joining different cables together, but also making terminations where you want to go from a normal material to a superconducting material. And we were able to show that at an operating temperature of 5 Kelvin, I forgot what field this was at, but I believe we did these at a range of different fields and very high currents. So we're looking at almost 30 kiloamps here, 30,000 amps being put through the sample. We were able to get joint resistances on the order of 3 to 5 nano-ohms, which sort of in superconducting cable land, single-digit nano-ohms is a really good number to hit. And also, an interesting aspect of this is that these joints, we didn't just put the joints together and put current through the cable and say, oh, great, we have a good joint. We cyclically loaded these joints, and so thousands of times. And so the bottom cable-to-cable joints experienced about 90 kilonewtons per meter of this I cross B Lorentz force and showed no resulting increase in resistance, which is really good. That means that, sort of thinking about the cyclic loading of joints, we made a joint that was robust enough to be cyclically loaded many, many times. And so Bravo, we also looked at the cyclic loading of the critical current. And so again, instead of just, putting the sample in, putting current through it once and saying, hey, the sample survived, we actually cyclically loaded it many, many times. So, 2,000 cycles of very large I cross B loads. So actually all the way up to 382 kilonewtons per meter this time, which is actually larger than we think the stack is going to experience in Spark. And we even did reverse cycles because we said, okay, the force is acting in one direction, but what if we reverse the direction? So we also reversed the direction of the cycles to make sure that there wasn't an effect that, that would happen in one direction where it didn't happen in the other. And as sort of a summary of these results, you can see there was a little bit of degradation, but the zero has been suppressed just so that you can see the detail. And if you actually expanded this out so that this wasn't a zero suppressed graph, there's very, very little degradation. It degraded around 4%. And then, and most importantly, the degradation, sort of within error bars appeared to stop. And so basically after you've cycled your cable, somewhere on the order of 10 times, 10, 20 times, that's the performance that you have for the rest of the lifetime of the cable. So this was really important because in some of the magnet systems in Spark, they would be cycled many times. And we needed to know that the cables that we made could survive being loaded with these I cross B loads under many, many cycles. So the third sample that we made, called Charlie, was actually combining both the I cross B loading and also putting strain on the straight cables. So, I mentioned before we had the purpose of this sort of circular sample was that in addition to the I cross B force that you get on the stack itself, there's a hoop stress that's on this hoop that wants to go outwards, and that gives you a strain that the cable would feel. And what we did, because we weren't able to use that facility, we said, okay, let's get clever and let's design a rig that will actually linearly strain these cables. And so we put them, I won't go through all the details, but we basically, we put these cables in special clamps. We used material called Invar, which has a very, very low coefficient of thermal expansion. And so it basically doesn't expand or contract when you get it hot and cold. And if you're clever about how you put that with the different steel pieces, which do have a coefficient of thermal expansion, and you're able to sort of clamp on to the cables, you can clamp and then strain the cables as you both cool them down, and also we use some hydraulic jacks just to give it a little extra to be able to get it to a strain state of actually 0.5%. So before I mentioned we need to get to about 0.3% for Spark. So we went beyond the Spark strain state, and then also loaded these to very high I cross B loads. And here's another one of these plots of cycles. Here's the performance, so the critical current of these samples. And you can see at the performance, there's a slight degradation again, and then it pretty much flattens out. So that was really good. And we actually, even the joints kept getting better and better. We were able to get just under 2 nano ohms in cell field of joint resistance, which is a really good result, especially because a lot of these joints that we had were reused between the samples. So not only were the joints robust, but they were reusable. And finally, the last test that we did, called Delta, was on quench detection. So we used a special fiber optic quench system using techniques from CERN and RRI, which is a lab in New Zealand, based on fiber Bragg gratings. So you have these fibers that you embed in your samples, and you can interrogate the fibers to actually measure heat pulses. And I won't go into all these plots, but basically, if you put an analyzer on the ends of these fibers, you can detect rises in heat. We put heaters on these samples so that when we had them cold, we could actually, sort of artificially induce a quench. And as we artificially, pulse energy into these cables, you could measure it on these fiber detectors to say, in a real magnet, you would have one of these and you'd say, there's some place in the cable that's getting hot. It looks like the system is starting to quench. We should turn off the power to the magnet so that it doesn't damage itself. And then we also were able in this test verify some of our models. So you have the pulse time of your heater and then the heating power. We were able, using the modeling that we had, we were able to kind of map the space out into a region where you're safe to quench, where even if you're pulsing heat into the sample, there's enough cooling to take it out. And then out here, if you go to the right of this cryostability boundary, you actually would have a runaway condition that caused your cable to quench. And we did intentionally quench the cable. We kind of edged up and sent it over into a quench zone once, and it happened almost exactly where the model predicted, which was really good. So at the end of the day, we basically, going through these qualities of fabrication, joints, I cross B loading, strain, and quench, we went through and kind of systematically knocked all these things out with these series of cables that we built, both for in-house testing and also testing at Sultan. And so the next step that we're working on right now is incorporating HTS technology into magnets at scale. So, now we've sort of built cables that are, on the up to 12-meter long cables. And now we want to build cables that are 100 meters long and actually build magnets out of those cables. And so that's what we're working on right now. And for this group, might be interesting is that although for us, we really care about magnets, there's nothing that says that this technology can't be used for other HTS applications. So things like transmission lines, superconducting motors, superconducting generators, there's nothing that says that these cables couldn't be used for that. Actually, we think that the fusion magnets are one of the sort of most stringent use cases of these cables. So a lot of other, transmission lines aren't going to see nearly, they're not going to see a big external field. They're not going to see the same types of strain and things like that you would see in magnets. So you could actually readily apply this towards something like that, or the motors or the generators. So really quickly, just to sort of recap what our plan is. So we have Alcator CMOD that was run at MIT and officially shut down in 2016. We've been working on getting the magnet technology to work. So we're building what we call the toroidal field model coil, which is one of these D-shaped coils. And that should be done sort of by the middle of 2021. And at that point, we're going to go into the second phase of the project, which would be building Spark, which is the Q greater than 2 demonstration machine. And then after that, we would go on to commercialization, which is this device that we call ARC, which would actually have a blanket around your vacuum vessel and actually put power onto the grid. And so Spark, which is this next phase, just a little bit more about that. It was designed using the same physics basis as ITER. So we basically aren't taking advantage of anything that, that the community doesn't know right now. We're saying use the same physics basis that ITER is being built with, but take it and use HTS magnets instead of LTS magnets to enable a device that's 20 times less mass and 40 times less plasma volume. And so the mission is to get Q greater than 2 with some pretty conservative physics, but actually if you map 1-to-1 the ITER physics basis onto Spark, you would predict a performance of Q of 11. But we want to under promise and over deliver. So we've designed the device. The mission is to get break even, a little over break even. So Q greater than 2, and you can do that with a very conservative physics basis. Just some plasma physics things. We're non-dimensionally very similar to those made in a device called JET that's in Europe. So we think that we're very confident that the plasma physics scenarios have already sort of experimentally been done, just not at this high of a field. We also, for the plasma physicists in the crowd, we operate very far from things like the beta limit and the Greenwald density limit because the field is so high. And importantly, we're going to have, we hope that, with the ITER physics basis, we'll have access to the burning plasma regime. This has been a goal of the fusion community for a long time to get to a burning plasma, and that's what we hope Spark will be able to do. And in the long term, very long term, we want to build thousands of these plants for the world. So, we would like to eventually have an effect on climate change and on mitigating climate change. And so we're not just doing this because the science is interesting, although the science is really interesting. But at the end of the day, we're doing this because we want to have an impact. We want to commercialize fusion and bring it to the entire world in time to mitigate climate change. So given that this is a student seminar, I would be remiss if I didn't include at the end a plug for CFS. Both CFS and MIT are hiring people. So if you're interested in being part of the effort, I would encourage you to, you can reach out to myself or Michael, who's also on this call. And then I can send the web links to the job postings, both CFS and MIT, which both has job postings and also postings for graduate students. So with that, I think I'm just about at time, and I would be happy to take some questions now.
Thank you, Brandon, for that fascinating talk. We have a few minutes for questions. I have several on the design, but I should probably let others go first. Questions?
I have a question about Spark. So If the blanket isn't very thick, are you worried about neutron damage to the magnets?
Yep. So spark, that's a great question. And we are very worried about neutron damage to the magnets. And so one of the things that makes spark work is that it's a pulse device. And the way that we mitigate the neutron damage is that the total runtime of the machine is not very long. It's somewhere around like 30,000 seconds. Each pulse will be about 10 seconds long. So we won't have, we basically won't have a lot of neutron fluence. But in ARC, we do have to worry about that, which is why the blanket has to be thicker.
Thank you.
Yeah.
If I can ask a quick question. Yeah, so the scaling, you know, the B to the fourth, sort of looking at your power density is sort of fairly well known. But one of the assumptions that power makes is that you've essentially got a flat density and temperature through the whole machine, and that you're literally utilizing the whole plasma volume to generate that power. But that is really not the real case. Are the high magnetic fields in any way, shape, or form going to help you achieve sort of that uniform temperature and density profile across the machine, or do you still need to work with other technologies in order to help with that, to really gain the absolute maximum out of your machine? Because just sort of with a lot of the work that I do, we do the lithium stuff, and a lot of these power regimes that people talk about, when you really look at it, the reality is they're not even going to come close, because you just don't have that. You're not utilizing your plasma volume enough.
Yeah, no, that's a really good point. So that, yeah, just for the purposes of illustration, that was just to show that, magnetic field is a really large lever, but the actual modeling that we've done to show the performance, for example, to calculate what we think the performance will be for Spark and for ARC, does use profiles that, that aren't flat and that are peaked profiles. Right now we're looking into seeing what the effect of having like a pellet injector would be in order to give us, a highly peaked profile. But our baseline assumption is that we're not being any more optimistic than ITER is as far as the profile shapes that they use. So we're saying that we're actually more conservative, I think, in some ways than the profile shapes that ITER uses.
So what would you say would be your maximum power you could generate for a reasonable size machine? So you had something was about 200 megawatt electric you're looking at, but if you want these machines to essentially replace your baseline, coal and gas plants, and even large wind and solar machines, you need to be getting it to something like a gigawatt base load. How big does a machine, let's say at 12 Tesla, need to be in terms of your major radius and that, in order to generate something like that?
Yeah, so
it would still be big.
Actually, with a major radius of about 3.5 meters, you can get to sort of gigawatt thermal levels of power, which is actually for coal plants. If you look at the retirements of coal plants that are happening, at least in the United States, they're sort of on the order of like 300 to 500 megawatt coal plants that are being retired right now. So appreciable fraction of a gigawatt, but we're looking right now at trade studies to see whether it would make sense to build like an island where you have several of these plants, so that you have one station that generates sort of gigawatt level, or whether you'd want to build a larger plant. But one of the things with the size, actually, just one more comment on that. One of the things with the size is that in addition to just being, less mass of stuff to put together, there's also a step change in a lot of things. So like one of the problems that ITER has is that some of their things are so big that they like literally require, like, road shipping things is not possible just because the size of roads isn't large enough. And so even if you had to build multiple arcs on a single plant, it would be preferable to building one large device just because of sort of the economies of scale of sort of the reverse economies of scale of different things.
Yeah. Well, they've had to use the rivers and stuff to send a lot of their mags, and I've been following their progress quite a bit. So,
yeah, maybe I'll jump in with one question on superconductors and the economics. So the LTS world has I guess MRI magnets as the kind of killer app.
Yeah.
And HTS, I guess the either ship is too large to steer. So curious about what you think is the killer app for HTS. Is it you guys? What quantity? For example, Spark, how much conductor do you use?
Yeah, Spark will use around 10,000 kilometers of conductor, which is by far the, if you sort of look at the HTS industry to date, it's really, it's existed for the last 20 years, but it's really only sort of existed for real for the last 10 years. If you look at all the wire purchases in the history of the HTS industry, it's been about 3,000 kilometers roughly that's been made. And so we require roughly 3 times that just for Spark. But the good news is that, and I've actually been really involved in this process, the good news is that the manufacturers want to scale. And because HTS, we think that Fusion is the killer app for HTS, not just because it uses a lot of it, but because it really requires it. A lot of the other applications, like transmission lines, HTS makes current transmission lines better, but it's a marginal increase, whereas really HTS magnets are enabling. If you want to have a very compact fusion machine, there's no other way to do it except without HTS. And so we're sort of forced to be, the first in the space to really go out to the manufacturers and scale them up. And they're starting to respond to that. We actually have ordered already for our magnet, the big magnet demonstration that we've made. We've ordered 500 kilometers of HTS, which was the largest that we know of single order that's ever been placed in the industry. That's already been ordered and delivered. And we've already seen economies of scale from that. And we have, we have manufacturers now who are signing up to say, we're willing to sign contracts that say, we'll get down to a certain price if you buy a certain volume from us.
That's great. We're running out of time here. George has left. Do we know if we can continue for another couple of minutes?
Yeah, I don't have a hard stop until 30 minutes from now.
Okay. Any questions from the students?
Yeah, I have a quick question. So where do you source your magnets from? I don't recall hearing that in the talk.
Oh, we actually build them ourselves.
Or sorry, the HTS tape.
Oh yeah. So there's several different manufacturers that we source from. Unfortunately, contractually, I'm not allowed to say who we buy sort of the majority of our tape from. Although I think in around 6 months from now, it'll be pretty apparent who we're buying a lot of our tape from. But we decided, just at a high level, we decided that we didn't want to pick just one kind of winner in the manufacturing space. If you look at sort of supply chain for anything, you generally want to have at least 2 sources, so that if, God forbid something happened, you have a fire at a plant or something like that, that you're not completely crippled. And also so that you can't get priced out by, if you have a single supplier and they know that they're the only supplier, then they can kind of charge you whatever they want. So, we've been developing the whole industry. We actually went out 2 years ago now at, one ASC, which is one of the big superconductivity conferences, and actually got all the manufacturers who go to these conferences. We got them all together and basically said, we're kind of throwing down the gauntlet. We're going to have, a very, very large order. We've raised, at that time, we'd only raised $100 million, but we have 200 million now. We've raised a large amount of money. A large amount of this money has been earmarked for buying wire. And, we'd like to be your customers. So show us what you've got and show us that you have plans to scale and to reduce the cost with your economies of scale. So several manufacturers have actually stepped up.
Thank you.
Mm-hmm.
Okay. Well, I want to be respectful of everyone's time. So maybe we'll wrap it up there. Brandon, so good luck to you on behalf of, I guess, all of humanity in your success, and hope to hear updates as you guys make progress. So thank you.
Yeah, great.
By the way,
thank you very much.
Are the slides available to be shared? Is that possible?
Sure. Yeah. Let me ask our PR person just to get their blessing. But I'm pretty sure that all of these should be able to be shareable.
That'll be great. Thank you.
Yeah.
Thank you very much.
Absolutely.
Thank you.
Yeah. Thank you. It was a pleasure.
Thanks, Brandon, and say hi to everyone over at Commonwealth.
Yeah, will do.
All right.
Take care.